All right, welcome to page 3 of the first day of notes for differential equations. And so we're just going to continue to classify differential equations by order, type, and linearity. So here we have the Newtonian dot notation, and so we have a second derivative there, minus 1 minus x, so the first order derivative to the second divided by 3 times x to the first derivative plus x equals 0. So the first thing that we're going to classify is the order, second order, because our second derivative is the highest. So second order. And then, is it an ordinary differential equation or a partial differential equation? We can go ahead and say ordinary because these are all going to be respect to the same, because it's like having y prime or y double prime. So it's ordinary differential equation. And this is going to be second, our first derivative squared. Can't have that, so it's nonlinear. Right, example 7. Determine whether the given first order differential equation is linear and the indicated dependent variable. So here we're actually going to take two. We're going to take one where v is the dependent variable, and then one where u is the independent variable. In v, if v is the independent variable, what I'm going to do is I'm going to multiply the equation by 1 over du, where in the denominator that is the independent variable. So in v, I'm going to multiply through this equation by 1 over du. So then that first part is just going to be u times dv over du plus, and then because all this is multiplied by du and I'm dividing by du, which is going to be plus v plus uv minus u e to the u equals 0. Now, I can already tell right now that this is going to be a linear, but if you cannot tell right now, what I suggest you do, because v is going to be the dependent variable, u is the independent variable. We're going to see that we have u, and then I'm going to say dv over du is just going to be v prime. All right. And then what we're going to have is we have plus v plus uv. I'm going to write that plus, and then I'm going to go ahead and pull out a v and have 1 plus u v, and I'm going to take the minus u e to the u to the other side and just have u e to the u. And now you might be able to read it a little bit better, where we have a first derivative of v with respect to u, a function of u times it, plus v to the first power times a function of u, 1 plus u, equals a function of u e to the u. So that gives us, it is linear in v. Again, that's the dependent variable. Now, if we made u the dependent variable, we're going to multiply by 1 over dv. So I'm just going to point this way so that you can see I'm multiplying by 1 over dv. All right, and so I'm going to do the work over here. So that first term is going to be u plus, and then we have v plus uv minus u e to the u, and then du over dv, and that's equal to 0. Hopefully now you're able to see, okay, here's my derivative. It's of the first order, but when I look at all my information over here towards the left, I have, v inside of my differential equations, inside the, function that's multiplying my differential equation. So that's what's making this nonlinear, is because we have a function of v inside of the, the term that's multiplying the d over dv, and there's no way I can fix that or, get it out away from that differential equation. So then it is, let me bust up linear in v, nonlinear in u as the dependent variable. All right, last thing we're going to talk about is something that's really not new. It's going to be solutions of ordinary differential equations. And so the definition, any function, again, I typically say phi, but you can also say this as phi. So I'll just continue to say phi because I think most people say it in terms of phi. Phi, the Greek letter phi, defined on an interval I, in possessing at least n derivatives that are continuous on I, which when substituted into an nth order ordinary differential equation reduces the equation to an identity, is said to be a solution of the equation on the interval. So we have our function of x, and then, phi prime all over the phi to the n is equal to 0 for all x and I, where I is called the interval of definition, the interval of existence, the interval of validity, or the domain of the solution. I can be an open interval, a closed interval, or an infinite interval. And ways that we can express solutions is we could have an explicit solution, which we talked about when we're taking the derivative. When we have the derivative and we're going back to the original solution, we'd have an explicit solution where we have y is equal to phi of x. And an example would be y equals x sine x squared. Right? So solutions of differential equations are just going back to the potential function, or the original function we got to get our differential equation where we took the derivative of it. And so another solution is the implicit solution, where you have a function in terms of x, y, and that's set equal to 0, or set equal to, set equal to 0, but then you can also make it set equal to a constant once you just solve. So an example that would be y sine of y plus x. Again, you dealt with implicit solutions before. And in order to take the derivative of that, you did implicit differentiation. So hopefully that should ring a bell. So those are two ways to share solutions to your differential equation. Your solutions to differential equations are going to be equations. You're going to go back to the original function, some we call the mother function, or the potential function, which is the best way to describe it, because you have to account for that plus c. And I'll talk a little bit about that plus c on the last page. And you also have the trivial solution, the solution of a differential equation that is identically 0 on an interval I. So an example that would be y double prime is equal to y. And that's true where it's going to be equal to 0.